on a disk floating through space with a tiny sun.
Hey, I'm FTFE. Welcome back to the channel that pushes stupidity down the stairs of knowledge. Today we are going to have a brief talk with Mitchell from Australia, who recently released... Sorry, 1 second. I am echoing back to myself. My bad. All right, so yes, Mitchell from Australia recently released a video which he claims debunks the globe model and its ability to predict eclipses. I challenged him on that on his video, and he's agreed to come on and talk about the models that we both have. So let's just get into it. Mitchell, welcome to the channel.
Hey, what's up? Thanks for having me.
No worries, thank you. I know it's very early there in Australia for you, so I do appreciate you taking the time. Bugger getting up at 5:30 in the AM for me. So thank you very much. Yeah, so I'll let you explain why you're here and what you were trying to say in that video, so we can just get into it.
Shameless plug first.
Yeah, go ahead.
I'm Mitchell from Australia by the same YouTube name, Mitchell from Australia. Up until recently, I was on co-hosting a podcast with Paul on the Plane called Dome Life. Check it out on all good podcast platforms. Basically, I want to talk about the globe model and its predictions or lack of it.
So the video that you made was specifically about the recent annular eclipse, right?
Correct.
And what was the issues that you had with that?
Well, in general, the globe model does not predict things. So that's where I want to go with this. I don't have to specifically keep with eclipses. I just want to talk about the globe model in general. Do you want me to give a bit of an intro? So
yeah, please go ahead.
My position. Well, I claim no model. Flat Earth has no model. There's no use for one. We don't need one. So I want to gauge your opinion on that. What do you think about Flat Earth having no model?
I think it's an issue because a model isn't like a toy or anything. A model is just a way to describe what's happening mathematically and something that's been proven via experimentation and its ability to repeatedly predict. It's not a physical thing. It's not like you can go and build a model of the heliocentric or the flat Earth. A model for me for the flat Earth would be a cohesive explanation for all of the phenomenon that are able to predict with an explanation what is going to happen. And the fact that the flat Earth can't do that, I see as a problem.
Correct. I couldn't agree with you more. We have no model, but you claim to have a model. And a couple of things you said then, predict things, experimentation, phenomenon, they're all scientific terms. So what kind of a model does the globe actually have? Is it a swimsuit model? Is it a runway model?
It's a scientific model. The scientific model of the heliocentric system is the combined explanations that we have that are able to make predictions. That's what a scientific model is. It's a very different thing to a swimsuit model or a model toy. It's just a name for a collection of explanations and predictions using the phenomenon that we have.
So an actual scientific model explains natural phenomena, as you said. So but it can only be considered as a scientific model if it can be objectively tested by experimentation. So what have you got to experiment on for your globe model?
All the measurements that back up what the globe model says, and the fact that it's able to make accurate predictions and cohesively explain everything that's going on.
Okay, so we've got two things there. We've got, well, we'll start with the prediction. What is a scientific prediction? In all cases of science, as the scientific prediction is the hypothesis. Do you agree?
No, the prediction isn't the hypothesis. You use the hypothesis to make a prediction.
So that's what a scientific prediction is: a hypothesis with an independent variable and a dependent variable.
They're not the same thing. You get your hypothesis, which has your IV and your DV, and you use that hypothesis to make a prediction about future events. The hypothesis isn't the prediction; they are different things.
Do you want to give us an example then? Start with the natural phenomenon and work from there.
Well, if you were I mean, obviously, when we talk about the scientific method like this, we're kind of talking about, middle school version of basic scientific method. There's way more to it than we talk about it in these conversations. But if we're going to talk about the basic middle school version of the scientific method, you're going to start with an observation, and then you use that observation to come up with a hypothesis, which is an educated guess, a presumption about what is causing your observation. And you use that to predict something that could happen using that hypothesis, and then you do experiments to test that prediction, and then you would analyze your results and, if need be, change your hypothesis. Do you want me to talk about any particular phenomenon, that we can apply that to? Because you can apply that to pretty much anything. You can apply that to the Earth turning. You can apply that to making a cup of tea. There's the scientific method described in that manner is a very basic guideline of how to go about doing scientific tests.
So you realise, I agree with most of your definitions, what we just went through, that scientific method, but do you know where the scientific model sits in the scientific method? Where do we get the scientific model from?
The scientific model comes from the collection of information that we have. All the explanations, all the experiments, all the equations, everything that all match up that are able to make the phenomenon. The model comes after you've got lots of different data that you can put together to be able to make predictions in the future. You can have very basic models that are able to just predict one or two things, or you can increase the variables and have it predict a lot more things.
Well, I'm glad we can agree on some things. So you have to do an experiment first, and then the scientific model is built from that. So I just want to say something about models. I think it's very convoluted that people think, as you said, it's not a physical model. It's not something physical. It's not something we can play with. It's not a toy. It is the result. A scientific model is the result from experimentation, and it's been validated by experiment.
Which is why I always object to, like when Nathan Oakley, for instance, will say things like, "We don't live on a model." Well, yeah, of course we don't live on a model. That's not, that's a big straw man that's used. So yeah, you do understand that it's not a physical thing. It's a collection of experiments and explanations and everything that give us a predictive ability for certain phenomena.
Correct. Okay. So do you want to actually go into something specific so obviously you've got a globe model, so it's been put through experimentation. What sort of experimentation, what natural phenomena has led you to this globe model?
So you want me to for instance, apply rotation of the Earth along the scientific method steps? I mean,
sure.
For me, my natural phenomenon, my natural observations would have been the sky that I saw when I was in the Royal Navy, looking at the way the sky acts as I move away from the North Pole towards the equator. For me, that suggested that we would be on a spherical surface. So my observation was the way that the stars behave in the sky, and my hypothesis from that would have been that the Earth is in fact rotating. You can have a dependent variable of the position of the stars, an independent variable of your position on the Earth, to actually make that basic observation, and you can make some predictions based on that. So if the Earth is rotating at the 15 degrees per hour that my hypothesis would suggest, then
sorry, I don't mean to interrupt, but you got two things going on. You got rotation of the sky and rotation of the Earth. Which one is the natural phenomenon?
Well, my observation was the way that the stars move, and my hypothesis from that.
Do you want to stick with that?
Yeah, but my hypothesis from that was that we are on a spherical object that's rotating.
So to have the dependent variable, you have to have one effect, one dependent variable. What are we picking? The rotation of the sky,
my dependent variable will be the position of the stars in the sky. That's something that could be measured, right?
The position or the rotation?
Well,
what are you observing?
Again, you're mixing up. My prediction is separate from the hypothesis, right? Based on my observation of the way the stars are moving when I'm traveling throughout the world, I have the hypothesis that we are on a rotating sphere, all right? My hypothesis for that would be the dependent variable would be the position of the stars in the sky, which would be the thing that you measured, and the independent variable would be my position on the Earth, which would be something that I could manipulate. So that's my hypothesis, is that we're on a rotating spheroid because of what I see in the sky. So then I need to make a prediction based on that hypothesis. So I've got my hypothesis that we're on something that is a sphere that rotates at 15 degrees per hour. Now I make a prediction. And my prediction would be something as simple as performing the Foucault's pendulum experiment at different positions on Earth and predicting the outcome of that based on the fact that we are rotating at 15 degrees per hour. And I can then do those experiments, see if I get the predicted amount of drift based on the Coriolis effect, and then see if that matches the prediction that I made based on my hypothesis. The thing is, your hypothesis doesn't have to directly relate to what your experiment is. Your prediction does.
Hang on, that's what you're testing though. The hypothesis is the experiment is in the experiment. You're testing the hypothesis in the experiment.
No. You're not directly testing the hypothesis. You are directly testing a prediction made via the hypothesis. You use your hypothesis to make a prediction, and then you design an experiment around that prediction. And so if that prediction is the hypothesis is an educated guess.
So does that contain the independent and dependent variable in the hypothesis, or is that in the experiment?
Well, they both have them. You have your IV and DV for a hypothesis, and your experiment has an IV, a DV, a CV.
Exactly. So you are testing the hypothesis in your experiment.
No, the IV and the DV in the hypothesis will not be the IV and the DV that are in the test, in the experiments. They're different things.
What's the point of having a hypothesis if you're not testing it?
You are testing it by making a prediction and testing that prediction. This is part of the issue that a lot of flat earthers have, is that they skip a vital part of the scientific thought process, which is to form a prediction out of the hypothesis. You take your hypothesis, which you have an IV and a DV to kind of give you a cause and effect relationship, but you use that hypothesis to make a prediction about future events. And it doesn't have to be directly related to what the hypothesis states. It's just something that would happen if the hypothesis is correct. So my hypothesis that the Earth is a rotating globe that goes at 15 degrees per hour, if that happens, then the prediction would be that a pendulum would drift a different amount depending on its latitude on Earth. So you've made a prediction from your hypothesis, then you test that prediction and relate it back to the hypothesis. If your prediction isn't verified, you don't get the results that you predicted, then you adjust your hypothesis and make a new prediction based on that adjusted hypothesis. But that's a very important part that's missed. This very important part that's missed when you guys talk about it, and that is that you have to have a prediction to actually be able to move forward and have the experiment.
So what are we actually doing in the experiment? Why is the Foucault pendulum coming to this? How does the Foucault pendulum work? Is the Earth rotating under the Foucault pendulum as it swings? Is that how it's working?
Technically, yes. It's got a fixed pivot point, and as the bob moves, each time it moves, it's maintaining its inertia from the position it moved as it goes backwards and forwards, which induces a drift to it. So the Coriolis force isn't things turning underneath, but in the case of the Foucault's pendulum, it's forced to turn underneath it because it's got a pivot point which is stationary with the Earth. And the fact that the bob is moving, you can make a prediction as to what the drift would be if the Earth is rotating at 15 degrees per hour. If it was rotating at 20 degrees per hour, you could make a different prediction and see what that would get. But because it's rotating the prediction at the hypothesis of 15 degrees per hour, you would predict a certain amount of drift that you would get. When you do the maths to actually calculate the Coriolis force induced onto the pendulum, that's the drift that you would expect to get. That's the prediction. So you test to see if that happens.
And so what happens when I launch my drone from this rotating Earth and the drone doesn't drift at 15 degrees per hour as the pendulum does?
The pendulum won't drift at 15 degrees per hour.
You just said the pendulum. What do you mean? What's drifting at 15 degrees per hour? Is it the
entire Earth? No, the entire Earth is rotating at 15 degrees per hour. A pendulum would rotate at 15 degrees per hour if it was on the North Pole. But as it moves down, towards the equator, the amount it drifts actually gets less and less and less. If a pendulum's on the equator, it wouldn't drift at all. That's the prediction of the heliocentric model and the maths. the Earth rotating at 15 degrees induces a drift depending on your latitude. You have to do the sine over the latitude times by the amount of time that the pendulum was drifting to actually calculate what that is.
We've
with a
gone off the
drone,
reservation of your actual experiment, though. Like, what are you actually testing in your experiment
my prediction
get to the globe model?
I'm testing my prediction.
Yeah,
if the Earth is rotating at 15 degrees per hour, then physics says
it's not the
that
Earth. It's to get to, sorry.
That's my hypothesis. That's my hypothesis. My hypothesis is that the Earth, the thing I am standing on, is rotating at 15 degrees per hour, which is the reason for the stars moving the way they are. That was my observation and my hypothesis from that. So then I've made the prediction.
Let's go from the top. So we've got an observation of stars rotating.
No, not rotating necessarily, just the way that the stars acted in the sky as I traveled throughout the world. And the measurements that I took of them using sextants and astrolabes suggested to me that I was on a spherical surface that rotated. All right. So using a measurement with a sextant. So how are you getting an angle with the sextant? Because what are you lining up? You have to use the horizon. So what are you lining up with the sextant? The physical horizon or celestial horizon? The horizon that you can see compared to the angle of the stars in the sky. And using the sextant and all the observations that I made, not just the sextant, but general navigation around the world that I did as a sailor, looking at the way the stars acted at different points on the Earth, and comparing it with the latitude that I am. All of my observations suggested to me that we had to be on something that was rotating. That was my hypothesis. All right. Your hypothesis could be, well, that means that the things in the sky are moving. Right. That would be your hypothesis. But my hypothesis was that I'm on something that rotates.
So all you're changing by moving location is what you're seeing in the sky. You're not actually manipulating what you think is rotating, whether it be
you don't have to actually manipulate what you think rotates. You have to change something in the to give your cause and effect relationship. And based on the fact of it's really not. Based on the fact of where I am on the Earth would mean that the stars would behave measurably different. So my dependent variable, the thing that I measure, would be the position of the stars in the sky based on my independent variable, my position on Earth. That would be how you would figure out the cause and effect relationship. But then that's just the hypothesis, right? That's just a guess. And a hypothesis is just an educated guess. So my hypothesis is that the Earth is rotating at 15 degrees per hour. Okay? That all my observations and everything that I've done, that is my educated guess. So now I form a prediction. So if I was to say to you, we've got the hypothesis of Earth rotating at 15 degrees per hour, what would you say could be a prediction for that?
A prediction? Well, I say the prediction is the hypothesis. You've got the independent and dependent variable. So you observe something.
They're different things. Prediction and hypothesis are different things. You have to separate them.
Have you got a citation for that?
Yeah, there's many. You can go to the first one that comes up is examples at yourdictionary.com. Difference between making a hypothesis and prediction. Hypothesis and prediction are both types of guesses. That's why many people get the two confused. However, the hypothesis is an educated, testable guess in science, as a prediction uses observable phenomena to make a future prediction. So you use your hypothesis and your observable phenomenon to make a prediction, which is the thing that you test.
So how is it that you come to the conclusion using this experiment that you're on a rotating globe? What is it what differentiates the sky rotating to the Earth rotating? How can you prove that
my prediction would be nothing to do with the sky. All right, there's no way the sky moving would make a pendulum drift. Yeah, but my hypothesis is that the Earth's rotating, so I'm going to make a prediction based on that. All right, so I'm making a prediction.
Only changed your location. So
yeah, I can change
location, you're not manipulating anything that's moving. You're just changing.
I'm manipulating a part of one of the variables in the experiment that would change the measure of the thing that you've measured. So, in this case, my position on the Earth, which is why I'm able to use the prediction of based on your latitude, your pendulum will drift
What's a
a
latitude,
different
though?
amount.
That's a presupposition on the globe. What's
No,
a latitude?
it's
Is
not.
that from Polaris?
We all know what a latitude is. They're the lines of latitude that are agreed upon by everybody. If the Earth is a globe, which has those lines of latitude, right? We're making a prediction here, and the globe has lines of latitude, so we're using that as part of the prediction. If the Earth is rotating at 15 degrees per hour, physics says that a swinging pendulum will induce a drift a different amount depending on the latitude it is. So you could do 5 experiments, 1 at the equator, 1 at the pole, and 3 in between. And you can make the prediction, well, if the Earth is rotating, based on the maths of Coriolis, at the equator you should see a 0 drift, an angle of 0. If, based on Coriolis, the pendulum is at the North Pole, then the math says that that will do 1 rotation in 24 hours, 15 degrees per hour. If it's halfway along, it will do about half of that.
Yep.
So
we
this
get it.
is the prediction.
The only problem is you're not actually manipulating anything. You're changing
I'm manipulating
location,
my position. Yeah.
That's not an independent variable. You're not
absolutely
manipulating anything.
I've manipulated the position I've done the experiment in.
We're definitely not.
I could also manipulate the time. I could make the independent variable the amount of time that the bob swings for. In experiments, time is usually an independent variable.
Not an independent variable. No, it's not. Otherwise, time would be the cause of everything.
I can give you hundreds of citations that say time is usually the independent variable when it's included. Time is absolutely an independent variable in science. It can be a dependent variable depending on the experiment. But time, 100%, is an independent variable in science sometimes. And I would challenge you to find me a citation that says it isn't, because I have hundreds that say it is.
Time would be the cause for absolutely everything if it was
not if that wasn't the thing that you were manipulating. You decide what the independent variable is.
You're not manipulating the course of time. All you can do is...
You're manipulating the amount of time in the experiment. Yeah, exactly. So you manipulate the time.
You can't go
It absolutely is.
It absolutely forward.
It absolutely is changing the time in the experiment. You manipulate something in the experiment, in this case, the amount of time. That is what you manipulate to change the measured phenomenon, which would be the dV.
All right, so we're not.
I'm sorry, but you're completely wrong that time can't be an independent variable. Again, I challenge you or anybody to find a scientific citation of any kind that says time cannot be an independent variable, and I will put it against the over 100 citations that I have that say it can be an independent variable.
No, so I'll have to get back to you on that. But at the moment, we can't go forward with this because I strongly disagree. It's not in the scientific method that you can use an independent variable as time or as a measure, as a location.
Where does it say in the scientific method that you can't use time or location as an independent variable?
Yeah, I haven't got a citation right now, but I will get back to you on that one. So I think we have to move forward.
Guarantee there isn't. Well, let's talk. Let's talk specifically about your video and the clip. Right. So I do have the video up here. Let me. Come on. There we go. Wow. So, just turn the audio off. I don't need it because you're here. So you are saying that we only saw a partial eclipse, right? That nowhere did we see the full the full eclipse, the full ring of fire and everything, right?
So did the globe model predict this? Was this a prediction, a scientific prediction from the scientific globe model?
Yes, it was.
Do you want to take us through that?
Yeah, based on...
I've got a citation. Sorry, just before you say, I've got a citation that says astrology is a non-scientific model. Do you want to? Can I send it to you?
Please go ahead and tell me how astrology isn't science.
This is from Johann Beecher from the 17th century. He's a chemist. Astrology, or the explanation of future events by the alignment of astrological objects, is an example of a non-scientific model, since the objective experiment to test cannot be devised. So how are you going to make an objective experiment to test whatever you think is going on? How are you going to manipulate things in the sky?
Science has progressed a lot since the 17th century, Mitchell, and astrology is 100% considered a science. Quite easily, you are able to test things by making predictions and see if those predictions happen. For instance, are you aware of how we made the discovery of the planet Neptune?
The planet?
Yeah. Let's
So
not argue about
begging the
definitions.
question
Let's
that
not
was a
argue
planet.
about definitions and begging the question and stuff, which I'm not. But
Well, no, you're saying that it's a
do you
planet.
know
So
do you know how we discovered what we know as the planet Neptune?
I don't really care. It's not got anything to do with.
It's a very good explanation of how the model makes predictions, and also a really good example of empirical experimentation and evidence. So
which model is this? Still
the
the God model?
heliocentric model, yeah, the heliocentric
The
model,
heliocentric model.
yeah,
So
which
how are
includes
we
the globe.
manipulating anything in the heliocentric model to produce
So
eclipses, to do anything in the sky? It's observation based. You can't
yeah,
actually experiment on anything in the sky.
Experiments and observation, if you read the scientific method. But anyway, so Uranus, we were making observations of the planet Uranus, and we noticed that at certain times in the year it did a weird wobble that wasn't explained by the maths that we had from Kepler and Newton. So what they did was, using the maths of Kepler and Newton, they made a prediction that, well, the math says that there should be a massive body about here that's exerting a gravitational pull. So if we, at this particular time, at this particular position, look in the sky at this place, we will see another planet. That was the prediction they made using the observation and everything that they had. They made a hypothesis and a prediction that there would actually be a planet in the place that they were about to look, based purely on the maths. And lo and behold, they looked in the place that they thought...
On maths?
On maths, yes. They looked in the place that...
What about the model?
And
what happened to the model?
Model is maths. So they looked at the place that the maths suggested they should, and they found the planet Neptune. That was literal example of empirical experimentation to explain a phenomenon and verify a prediction. And maths is very important, because maths is actually how you make your model, and maths is how, in science, you prove your ideas.
Incorrect. Maths can't prove anything. Maths
no,
is
math. It's
not
incorrect. Maths is literally the only way that you prove things. Science doesn't prove things. Maths does prove. Maths is where you find proofs. This isn't something that's up for discussion. This is a fact. Maths is how you prove your ideas in science, according to science.
What's the empirical method? The empirical model here, is it science or is it maths?
Science is how you prove your ideas.
So you can prove things with science.
No, you prove your ideas with maths. Science gives you the explanations and the experimentation and the method of doing things. You prove things with maths, and that's not really an argument I want to go back and forth, because I've done it so many times. It's really not. If you do just a little bit of research around the subject of scientific proof and what maths does, you will see that within science, maths is how you prove your ideas. That is just a fundamental fact of science. It doesn't matter if you disagree or not, because it's still true.
Well, it's not me disagreeing. I've got two citations here. One from Richard Feynman. If it doesn't agree with experiment, it is wrong. It doesn't say anything about maths there.
Yeah, not didn't say about proof either, did it?
From Max Planck, experiment is the only means of knowledge at our disposal. Everything else is just poetry, which is what maths is.
Again, it didn't say anything about proof there. Proof is a very specific thing, and the only way to prove your ideas is by using maths.
So the only means of knowledge at our disposal is experiment.
I didn't say knowledge, I said proof.
So what's proof? It comes after we know something. That's how we prove things, through the scientific method, not through maths. You
literally use maths to... You literally use math to prove ideas in science. This is what science says. That's how science explains its ideas, is by using maths. And again, it's not something we need to go back and forward. It's a kind of a mute subject, because the slightest bit of research will show. Yeah, but how do you prove? How do you prove your ideas with the experimentation? What do? You use math to describe what the experiment showed. You prove your ideas using maths. And this is just a fact of science that really
is a description. It's a language, so that
and it's how you prove your ideas in science,
through experimentation, through testing your hypothesis, or what you say, your prediction. So you've got the independent and dependent variable, and you're verifying, you're validating that prediction, aren't you?
Yeah, and you prove your ideas with the math behind it, because the science gives you evidence for something. Yeah, the science gives you evidence for things, and you prove that ideas, that the evidence and everything by describing it with maths. You know, that's
what
literally
kind of
how it
evidence
works.
you get? You don't get mathematical evidence, you get scientific evidence.
Yeah, and then you describe that evidence using mathematics. This is how
Correct,
you do
describe
scientific
it, but
papers.
that's not the
Yeah,
proof.
and that's what the proof is. The proof is the descriptive element of it using mathematics. That's literally what proof is. Because science does not prove things, maths does. And that, again, that's just a fact of engineering and science that anyone that's involved in engineering and science has lived their whole life by, and what they have to do, because maths is your proof of your ideas and your evidence and your experiments. It's just how it is. Let's get back to your video, because some of the things you said, like for instance, you said it didn't make the, this is what it predicted on the left here, and this is what I saw on the right, but that matches what you're seeing there. So I was slightly unsure as to why you were saying that both what you saw and what NASA saw weren't the same, when that prediction exactly matches what you're seeing there.
What sort of prediction is that?
Well, it shows you the prediction of where you should see the totality, and it's just touching it. And as you can see, it's obviously turned slightly because of the position you were, but there's that bit just on the side where it was just touching it. That matches the prediction of what you were going to see at that position.
Specifically, I said the globe model cannot predict eclipses. So
but it predicted this one
after proving your prediction, correct? So how does the globe model predict something before you've even proven it?
Because proof is, I don't think you know what proof is. That's the problem. A prediction is something that you're predicting that is going to happen in the future, and you would use maths again to make that prediction.
The model is formed. So it
doesn't. It doesn't come before the model is formed. The model is formed to make predictions. So anyway, let's talk about what you said in your video, Mitchell, because this is very important.
Yeah, exactly.
You said that this doesn't match the prediction, but it made the prediction and it matched it. So how are you saying that doesn't match what is showing when it literally does?
So do you want to use this as a kind of the scientific method here? So we've got an observed natural phenomenon. So we're observing something in the sky, and what would you say in the hypothesis or your prediction, whatever you want to call it, what would you say is the independent variable?
But we're not. This isn't a scientific experiment or a hypothesis we're doing.
This is a prediction.
No, this is a prediction that came from the model. So you don't need you don't need hypothesis and stuff to do that. This is just a prediction that came from the model. And you're skirting around the issue, Mitchell, which is what your words were, that it doesn't match the prediction. But it made the prediction and matched it exactly.
So you have to listen to and read what my actual words were. The globe model does not predict eclipses. You can't use the globe model to predict things. So we're going the opposite way here.
But it did. No. Your words were talking about this. You were saying, look at this scientific prediction, which isn't scientific, by the way, and look what I got. It doesn't match. And then you went on to say that even NASA didn't get what they expected when NASA got exactly what they expected. And then you went on to say that nowhere did we get an entire ring of fire, which we did. And this is all based on the heliocentric model.
Just interested, do you actually have a ring of fire?
Yeah, hold on, here we go.
Peeking through the valleys between the mountains there. It's doing it at the top now and at the bottom, and then it catches up. These are called Bailey's beads. You can see a few at the top.
Right, I'll just show it to my audience.
Brian mentioned them in his talk, so we're getting a very good effect there. There's a whole string of Bailey's beads coming now, look, all round, and it's going to very rapidly join up right round to the full ring of fire.
Ring of fire, there it is. So was that predicted by the globe model?
Yes, absolutely it was.
It was? So you've got the globe model before the prediction.
The globe model made the prediction.
So let's pretend...
Wait, Mitchell, do you not know what... We talked about what models were. Models are something that you can use to make predictions. This was the prediction made using the globe model, that this would happen.
You're convoluting what a model is and what a
No, I'm not. A model is something that makes predictions. You can use the model to predict the position of eclipses. That's exactly what a model is the heliocentric model.
So what is in, like, does the heliocentric model explain everything?
Every natural phenomenon that we can see, that it explains pretty adequately and predicts them. And it predicted this. It predicted this exact thing, which you said in your video didn't happen. Can you at least admit that you were wrong about that?
Listen to my words. Predictions come in the hypothesis. You can't have a model first. The model comes
a model is what is used to make predictions. That's how it is a model, because it has predictive abilities.
The prediction comes from observing the natural phenomenon. So if this is a natural
phenomenon, no, it doesn't. In the scientific method, a prediction comes from the hypothesis, not the observation. You're wrong about that. And a scientific prediction that comes from a model isn't the same thing as a prediction that comes from a hypothesis. Just because they're the same word doesn't mean that they have the same attributes to them. You use a model of any kind to make a prediction. That's the purpose of a model. Right, we have this model that explains everything. Now, we use this model to say, well, this would happen at this particular time, and this is why. You use the model to make a prediction, which it did. So the globe model absolutely does make predictions, because it made this prediction accurately.
So you've voiced your opinion on what's going on here and what you think's going on. Can I voice my opinion?
Please do.
Without being interrupted. So if we're putting this through the scientific method, you do observe a natural phenomenon, and that's what your prediction or your hypothesis is based on. How can you say that you don't observe something and then test that to get the effect? You have to observe something, you propose what is the cause of that thing, and then you experiment on it. So you absolutely have to observe something first. So if we're observing an eclipse, you propose the cause to the eclipse. Now, what's the cause to the eclipse?
Well, it would be the moon going in front of the sun.
Okay, and how can we manipulate that?
By changing the position that would be on Earth, and that would change the actual amount that the moon would be covering the sun.
Yeah, I see why you went with positions, because that's not actually manipulating. You can't go backwards.
It absolutely is. It doesn't matter. That's not what manipulating means. Manipulating just means changing the variable. It doesn't mean physically going and touching it. Don't be Anthony Riley. And again, you are conflating a prediction formed from a hypothesis and a prediction that is given via a model. Because there has been many eclipses in the past that we have managed to correlate in information and actually create a model around a lot of other things, we can now use that model to make predictions. That is literally what a model is for. So we predicted that this would work.
Can we focus on that word, correlation? Because I'm talking about causation in the scientific method. So you've got correlation. So you're observing a pattern. That's how a Mystic Meg prediction works.
It's not just a pattern.
Prediction works.
That's a straw man, because it's not just observing things. It is a collection of experiments and data and all the knowledge that we have gained to be able to create this model. And the model will change over time as we gather more and more information. It can become it has become more accurate over time. That's literally what happens as we get better at doing science. But it's not just observing patterns. It's giving explanations for them. It's explaining the physics behind them. It's been able to use our understanding of the physics and everything around it to make accurate predictions down to the millisecond and the millimeter of where and when we can view a ring of fire.
So that's correlation, like you said. It's not causation. That's not scientific method. So it's got nothing to do with science.
You have to use correlation to gather information.
No, you use observation, and then
but then how do you take? Wow, you just skipped like 4 sections. But how do you take notes of that information? You correlate it. You would put it down and go, well, okay, this matches that, which matches that, which matches that. So let's do some experiments around this. And after years and years and years of collecting information, looking at things, doing experiments, testing different hypotheses, you can create a model, and that's been done. And once you've got that model, which has been done, you can then use that model to make predictions and see if that comes out. If you like, you can go and start science all over again and try and create a new model based on the observations that we have now. But that's already been done.
Let's do it with other things. Let's see what the model predicts about the black swan observation, about the radius value, about terrestrial refraction.
Yeah, it predicts that exactly. Our model, which includes refraction,
the black swan observation.
Yeah, the heliocentric model includes refraction and makes that prediction. Mick West actually, using the heliocentric model, showed the predictions that are available. So because refraction and the way that light bends is part of the heliocentric model, the black swan is explained perfectly and predicted by the heliocentric model.
So the black swan absolutely debunks the radius value, which you use
in
terrestrial refraction, 706R.
No, it doesn't.
So where are you getting the R value if you haven't got an R?
You don't need to see the horizon to get a radius. That's a very silly thing to say.
Okay, how are we getting the radius then?
Well, you can measure the divergence of plumb bobs.
Plumb bobs. How are we using the plumb bob to get a radius?
Well, you can test the divergence. It's quite easy. You do some maths.
Divergence?
Yeah.
Enlighten us.
Well, the fact that plumb bobs lean away from each other, you can use that to easily calculate your radius.
Where do they lean away from each other? So you got two places at once and you're seeing a leaning plumb bob.
Yeah, MC Toon's actually got a good experiment that Jesse Kozlowski and the main surveyor did. But we can talk, the most famous example is that there is...
plumb bob.
Yeah.
How can you ever see a leaning plumb bob? You're only presupposing that in a different location compared to one location,
you measure
it's going to be leaning from that second location.
You measure it.
A leaning plumb bob.
Oh, you say you can't measure it, but it's been done. You can measure
a leaning plumb bob
by reciprocal zenith angles. It's quite easy. I can show you the information. It's all on MC Toon's page, mctoon.net/curve.
Fantastic.
Where again, the main surveyor has done, I think, 3 of them, and Jesse Kozlowski done 1. But one of the most famous examples is the Vera Narrows Bridge in New York. A very important engineering part of suspension bridges is that the support towers have to be perfectly plumb to be able to cope with the variations in weight between when the cables contract and expand with heat. And because the towers are completely plumb, you can measure them, and the top of the towers are 1 5/8 inches further apart than the bottom of the towers, showing that they are leaning away from each other, matching the predicted radius of the globe. So you don't need to see the horizon to be able to...
when he was looking... Okay, well, we get it. I'll look through it later. So Al-Biruni, when he was looking at the horizon to measure the radius, was he wrong then? You don't need the horizon. You can't use the horizon. It's refractive.
I didn't say you can't use it, but you don't have to use it.
Why don't we use it? It's there. We don't need to build bridges.
Because it's kind of hard to... Well, you don't have to. That's just a good way to do it. It's kind of hard to do it optically like that because refraction is a thing.
So you can't see physical Earth curvature.
You can see a refracted version of it. The fact that there's a horizon is because of the curve of the Earth.
What's things disappearing bottom up from then? It's not physical Earth curvature.
It's still going over the horizon.
What's the horizon? Is it physical or is it optical?
It's a refracted part. Everything you see is refracted, but the horizon that's the horizon that's there is just a refracted version of the geometric horizon, and you see things go over that just like you would expect to. Again, the refraction is part of our model. That's all explained within our model because of our understanding of light, thanks to Newton, who was the one who basically did experiments and quantification of refraction.
So it's not a physical... The horizon that we're seeing is not physical. It's refracted.
Nothing. You right. Hold your hand out in front of you. Is that your physical hand you're seeing?
Correct.
No, it's not. There's an atmosphere. There's atmosphere between your eyes and your hand. You're not seeing your physical hand.
Atmosphere. You're seeing your just air. We're
atmosphere.
Not the question of
it's called the atmosphere. It's called the atmosphere, and we're just going to call it that. But there's atmosphere between your hand and your eyes, which means that the light between your eyes and your hand is refracted, which means you're not seeing your physical hand. You're seeing a refracted position of your hand.
So is there anywhere we can actually see the physical Earth horizon? You know that thing that Mr. Sensible did where he sent up a high altitude balloon and he claimed he saw Earth curve? Is that seeing Earth curve?
Yeah, because when you're up at that height, you can see at the top of the atmosphere, which curves with the Earth, showing the Earth curve.
Can you show us air that is in a shape? There's no atmosphere, and if we're looking at the
gravity is
horizon,
a thing. Which would have to go through this. Gravity is a thing, and it causes the atmosphere to stick to the Earth.
Do you want me to turn my kettle on and I'll watch the steam go up? And gravity has no
as the predictions of gravity say, yes.
So gravity works sometimes and not always. So gas
no. It's because of gravity that the steam is going up, because buoyancy is a thing.
It's because of gravity. So
yes.
what is gravity? I thought everything went down.
That's just because you're ignorant. Buoyancy is a force that can act in the opposite direction to gravity. But an important part of the buoyancy force is the downward acceleration g of gravity. Rho equals force of buoyancy equals rho vg, or rho gv.
So it's all got to do with just density then, relative density.
No, I didn't say nothing. There was density.
So what's buoyancy? So what's the gas doing? So it's not being pulled down.
As I just said, it's rho gv. So the force of buoyancy, which is the force that acts in the exact opposite direction to gravity, is the rho, which is the density of the medium, times g, which is the downward acceleration of gravity, times v, which is the volume displaced by the object. So buoyancy is because of gravity. That downward acceleration of gravity is what causes the buoyant force in the opposite direction. Let's, for instance, just talk about a helium balloon and air quickly, right? So a helium balloon is less dense than the air and has less mass than the
density.
air.
So
wait, hold on. That's just one of the variables, right? But the air has more mass and more density than the helium balloon, which means, according to Newton's law of gravitational attraction, the air has a stronger force being applied to it, which means that it is pulled down with more force than the balloon, which makes a force in the opposite direction for the balloon, because things that outside of the balloon are being pulled down with more force. That is the predictions of the heliocentric model. So I just want you to understand.
I understand what your
all buoyancy, everything that you talk about buoyancy going up, that is part of the predictions of gravity.
Of the globe model. So
of the heliocentric model, yes.
Okay, so the heliocentric model. So how are we having this air, this gas, without a container? How is it being contained here?
Gravity is the container. Gravity is the container in the globe model. Yeah.
So that's been put through the scientific method, obviously.
Absolutely. I could give you 5 experiments right now. Say Cavendish, Schehelian, Pound-Rebka, the discovery of Neptune, and the Eddington experiment of 1919. All follow the scientific method and demonstrate gravity matching the predictions that you would see.
Well, what if I can do a scientific experiment that doesn't need gravity? That's only density.
Well,
Anthony Riley's egg experiment.
That needs gravity.
It doesn't need gravity.
It really does.
We're just adding
you
mass.
don't need to presuppose gravity, because gravity is part of the buoyancy equation. So when you add mass, when you add mass and change the density, you are changing one of the variables in the buoyancy equation. That's what he did. All he did was change a variable in the buoyancy equation, which already has gravity as part of it.
It's nothing to do with buoyancy. There's nothing to do with gravity. All you're doing is
sorry. So are you saying are you saying that he didn't change the density of the medium?
That's exactly what I'm saying. He changed the medium.
He changed one of the variables in the buoyancy equation, matching the predictions of the globe model.
You can say it all you like. We're not agreeing on this.
I mean, that's because you don't understand how maths works. I don't. It's not your fault.
Maths, so it's nothing to do with science.
Maths, physics. Well, maths is a lot to do with science. It's the language of science and how you prove your ideas in science, and how you explain physics and chemistry and everything in the universe. But no, Riley's egg is a perfect example of the buoyancy force due to gravity. You change density, you change one of the variables in the buoyancy equation, as the prediction says, and you cause an acceleration. Density isn't a force. We know that. Mass over volume isn't a force, but gravity is a force, buoyancy is a force, and these things cause the acceleration that you see.
It's got nothing.
Very simple.
I'll just put it through the scientific method. So we observe something, an egg in water. It floats. If it's in salt water, it floats more than fresh water. So we can experiment on that. We've observed that. So the hypothesis is you cause the egg to move in the medium by changing the medium. So he's changed the medium in the experiment. He's added mass, changed the density of the medium, and the egg moves. No gravity needed.
So where was your prediction? You gave me a
same thing as the hypothesis.
They're not. They're really not. You gave me your hypothesis that different. So what is the hypothesis? That different density of liquids will change the position of the egg, right? That's your hypothesis.
Dependent variable is the egg moving. Independent variable is the mass.
Is the mass or the density?
The mass, introducing mass to the medium, changing the density.
Right. Okay. So you're just assuming
you're manipulating.
Wait. You're just making the assumption that it's density there. I think it's just mass.
What do you mean? It's just mass.
That's how stupid you sound, Mitchell.
Density of a volume.
Yeah, and exactly. So you are accepting one part of the equations, that the density is mass over volume.
I'm not accepting any part of any equation.
Well, you just accepted that density is mass over volume. That's an equation. You just said that. So you accept that part of it.
I didn't say the equation.
You said mass over volume.
It's got nothing to do with it.
You said mass over volume. That is the equation.
We're changing the mass in the density in the medium to change the density. Yeah. So and then we see what was predicted.
So how would you calculate what the density is?
Why would you need to calculate it? You've proven it scientifically. You've manipulated.
How did you prove it?
What
maths did you use?
We don't need maths. That's where you go. That's where
maths proves you. If you're saying prove, you need to use maths.
No, you need to use science.
And you started by saying you changed the mass. You didn't say I changed the density. And then I said, well, I think it's just mass. And then your words were, well, density is mass over volume. So you were the one that brought up the maths and the equation. You cannot do these things without considering the maths. And if you accept one part, of course I'm scientifically illiterate with my degrees in science and stuff. Of course I am. Successfully operating nuclear reactors for years. Of course I'm scientifically illiterate.
Because it defies your religion of a globe model.
I don't have a religion. I have experiments. Yeah, no, science doesn't prove things. Do you know what kind of science does prove things, Mitchell? Do you know what kind of science does prove things, Mitchell? Pseudoscience.
All science.
Are you a follower? Are you a follower of pseudoscience? Because if you're saying that science proves things, you are a follower of pseudoscience.
So now we're projecting, aren't we? So you're saying
no, not at all. You're saying that science proves things, and that isn't science. Science does not prove things. It's as simple as that.
The only means of knowledge at our disposal is experiment. How can we know things? How can we prove things without experiment?
Knowledge and proof are different things. Knowledge and proof are different things.
They're different words, but how can you have
they're very different things.
Proving something?
Well, that would mean that having a prerequisite of having knowledge is having the proof, which would mean using the maths.
Math has got nothing to do with it. You use the scientific method to prove things. So
scientific method doesn't prove things. Find me a citation that says the scientific method proves things. You won't, because it doesn't.
Absolutely, I will. So I've got a couple of minutes left. Is there anything you want to go back over?
Do you accept that you were wrong in your video, that there was no complete rings of fire?
No, I said that the globe model does not predict eclipses. Correct.
Your words in your video were, I want a glober to show me one because there aren't any.
Yeah, because I want to talk about your globe model and how it doesn't predict.
So you were lying in your video.
Comes before.
You were lying in your video then, were you?
The prediction that you've said comes before the model. So if we're using that observation,
we've already got the model though. We've already got the model. We've done that already.
Pretend. Let's stop begging the question and pretend you didn't have the model. Let's put it through.
Not begging the question. I didn't beg the question at all. So please don't strawman me because. Well, I don't need to pretend that because we've already done that part of science, and I don't intend on starting science from scratch.
Can we use this observation to get your model? If yes, you put it through the scientific method.
You could do, yes. You could say what is this observation and form a hypothesis around it.
The observation of an eclipse.
Yeah, all right. The observation right. So this observation, all right, this ring of fire. So we see this, all right. What would you suggest as a hypothesis for this?
I don't need to because I'm not trying to prove it, but your model does. That's the problem.
I'm not trying to prove anything again. But all right, let's just talk through it
Because you think
together.
it's maths, so
It is. Let's just talk through it. Let's just talk through it together and see if we can get there together. All right. So, if this is the observation that this ring of fire happened, what would the hypothesis be? What do you think it would be?
I don't claim.
Regardless of whether you claim it or not, let's just work through it together. What do you think the hypothesis could be?
Yeah, you'd like me to say what it is, don't you?
No. I would.
But your model does.
I'm not asking. I'm just asking you to hypothesize. Make an educated guess. That's what hypothesis is.
I'm not putting this through the scientific method. You're trying to
trap
me into something.
That's what the scientific method is. This observation.
What it is.
This observation. What would be the hypothesis drawn from this observation?
Yeah, that's your claim. What the hypothesis is. I'm not claiming I'm not claiming it's science. You are. So what's the hypothesis? You're projecting.
So you don't know what the hypothesis would be, is that right?
There is no hypothesis. What can we test? What can we manipulate to make this different?
We can easily change our position to see if it is what we suggest it is. My hypothesis from this would be that the moon is passing in front of the sun and blocking out 95% of it.
And your experiment would be changing position, which is not an independent variable.
Incorrect. Find me a citation that says position cannot be an independent variable.
Absolutely. All right. Well, that's all I got time for. And that's
you can't, Mitchell. You cannot do it because I've looked and there are citations that say that position and time can both be independent variable, and there is not a single one that says anything else.
We'll leave it as that. Thank you for having me.
Thank you. All right. I'll catch you later. Have a nice day.
Bye.
Bye. Well, there we go, guys. Nuh-uh. I don't understand science. You're wrong. Time can't be an independent variable. Position can't be an independent variable. You can't go backwards in time. Flerf 101. So he made a bunch of lies, right? Because the first thing that he says in his video is that the globe model is broken because he thinks that it can't make predictions, which is obviously exactly what it's for, right? And in his video, he's showing the position that he's at and that they watched the eclipse. And he says that this is the prediction that the scientific thing made, even though it's not science, because he doesn't understand what science is. And then on the right is what he saw. And as you can see, it's touching it just on the left, on the top left there, which is the bottom left here, because it's shifted around because of his position. But that matches the prediction that he says that he had. And then he straight up says in the video, it doesn't match the prediction, even though it does. And then he says the same thing about NASA. And then later on he says, oh, there's all these semi rings of fire, none of them connecting completely. But then we've got this, which shows that it actually happened. This is from the Cambridge University Astronomy channel. So there we go. Another flatty, thoroughly dismissed and destroyed. I hope you enjoyed an early debate. There will be another one later with a complete and utter dumbass that was on MC Toons last night called Horatio. A horrifically horrible piece of human trash, as so many flat earthers tend to be. Time to read super chats and get out of here for now. I think you guys are amazing as always. Wow, 700, 800 watching. That's incredible. A whole lot of nutter. That's right. Let's see who there. Solarian Castle, Stephen Cook, YouTube Surgeon General, Heat Shield, Clive Wells. Never underestimate the stupidity of a Flerf. Yeah, really. So anyway, super chats. Buddy Zappy for £5 says, once again, Craig, you've reached the bottom of the barrel, dug through the Earth's core and broken through to the bottom of a barrel in Australia. Yeah, I thought Mitchell would bring more than nutter and not understanding the scientific method. That's the same conversation I've had 1,000 times. A new member, you fucking awesome person, you. Dead last zombie. Welcome to the Scrappers. Canadian, $5 Canadian from Perth. Please don't confuse astrology and astronomy. It's offensive. Yeah, astronomy isn't a science. Scientists disagree. Second best Bob for £10. FTFE, keeping the world real. Rock on. And then Pentalica, $5. Regarding Riley's egg experiment, if gravity was the thing, what if gravity wasn't a thing, what would the results have been? If gravity wasn't a thing, it would just floated around because there'd be no reason for it to be pulled down to Earth. Philosopher King Gaming for $2. See you for Horatio Destruction later. Yes, if you want to see a dumpster fire, please come back in a couple of hours for me destroying Horatio. If you want to see Horatio in the meantime, go and check out MC Toon. He destroyed him yesterday with me there. It was fun. But yeah, for now, that's it. See you guys later. Hope you enjoyed that brief destruction of Mitchell from Australia. Remember, stupidity is not a right. Fight the flat earth.
Fight the flat, fight the flat, fight the flat, fight the